Hey everyone, in this video I'm going to cover some of the basics of monitoring processes. There are a lot of tools available for working with monitoring systems resources that are included with most installs, but I'm going to try to stick to keeping it simple and mostly cover the core basic tools. When it comes to processes, certain aspects of the topic are pretty in-depth and complicated. I'm planning on keeping it somewhat basic, so there'll be some very simple explanations when it comes to the more complex topics. I may follow up in a future video and dedicate more depth to some of these topics that will only be briefly covered here. Start off by checking out the uptime command and a quick intro to load average. Load average displays three comma-separated figures, as you can see here. From left to right, it represents load over the last 1, 5, and 15 minutes. These values provide an idea of how busy the CPU is at specified intervals. The meaning of the values is interpreted based on CPU physical cores. We can find that total number here in the LS CPU output. So here we have two total CPUs on the system. Simplified explanation is that it describes processes waiting on CPU time, or it can also be looked at as CPU idle time. 0 indicates idle. A value of 1 indicates that a process is currently fully utilizing one core or CPU thread. So with a value of 1, if I have two threads or cores on the system, that means I have one core at idle and the CPU is roughly 50% utilized. So at a load average of 2, consider the system to be 100% utilized. If that value goes above 2, then the system now has processes waiting on CPU time. Remember, this scales depending on the number of cores. This is a quick way to do a general check of CPU utilization, but not particularly helpful to identify the process or processes causing increased CPU demand. We'll have to use other tools to help us determine the cause. So that brings us to the PS command. One of the tools that can help us investigate processes is the PS command. The man page gets into some detail about the different ways to pass options to the command. These are the different option styles that the command takes. I'm going to stick with the Unix options for this video. The PS command by itself will show all processes of the effective user ID. Here we see the processes running for my current terminal, bash, and the PS command itself. The process ID is returned along with the terminal it was executed on. The time field meaning CPU time, which is the time the processor has allocated to the process. Last, the command field, which is the name of the process. So by itself, PS is helpful for tracking processes running from the current session and also shows processes or scripts running in the background. Running the sleep command and setting to the background, it now appears in the output of the PS command. So sleep command ran for the specified amount of time, then outputs a message on the terminal the next time the prompt is returned. I plan on covering job control in the future video. PS command can also list processes for a specific user or a list of users. A quick mention that different options and combinations may return different results related to the UID. In particular, some options return the RUID and others return the EUID. The real user ID is the user that created the process versus effective user ID, which identifies the user permissions applied to the running process. So running by itself, it returns for the current user and provides similar information to PS without any flags, with some additional fields. Or it can be used against a specific account. And so we get all the processes running for root. Or you can provide a comma-separated list of users. Command has different options that return all processes. I'm going to use the Unix style with AUX. In this instance, the options I used A, give me all processes with a TTY. U, used with A, return all TTY processes for all user processes. And X, return processes not running from a TTY. Now that we have all of our processes, there are some fields that we haven't talked about yet. I'm going to skip the fields that we've covered earlier. So user, obviously that's the account it's running from. We have the ID of the process, the percent CPU, and that's not a measure of the percentage of CPU utilized now. It's a measure of CPU time divided by the time the process has been running. Percent of memory, which is the current percent of physical memory occupied by a process. VSZ, virtual memory size in kibibits. RSS is resident set size, non-swapped physical memory that a task is used in kibibits. Stat is the process state, and there are several state codes that are also sometimes combined with additional characters to indicate additional information. So I'll run through and just give a quick high-level description of the codes. They can also be found on the man page. D is uninterruptible sleep, usually a process waiting until a resource becomes available or a timeout is reached. I is idle kernel thread, in a standby state waiting for something to do. Are running or runnable, either running now or ready to run, waiting for CPU. S is interruptible sleep, process is waiting on something. T, stopped by job control. Z, zombie process, the very short explanation is a terminated process not cleaned up by the parent process. Lowercase t, stopped by debugger during tracing, the quick and short related to using debugging and diagnostic tools. The additional characters, some of which you see here, have the following meanings. A less than sign means it's high priority. Capital N is low priority. Might see a capital L. Has pages locked in memory to keep it simple. Considers to be tied to something a program or a kernel has requested to keep in memory for time-sensitive operations. There's a little bit more to it, but we're not going to get into the details there. A lowercase s is a session leader, and it's a bit of an oversimplified explanation, but high level. It is a way of grouping processes. I'll include a link to a reference resource if you're curious about getting into the weeds on that topic. And a lowercase l means it's a multi-threaded process. A plus means it is a foreground process. Of course, we have start, which is the time the process is started, and the rest of the fields were covered earlier. So there's a quick rundown of grabbing all processes. We can also get specific processes and control the output fields. And so with an uppercase C, it will return the process information by command name. So if we could do bash capital C, bash. There's also a way to return specific fields with dash lowercase o. So we can still do the uppercase C with bash as our process. And then we can include that parameter with the arguments, with the field names we want to include. And that way we can do specific filtering or report on processes however we'd like. You get a full list of fields from the man page. There's quite a few of them that you can specify there. We can also provide a process ID prepended by a dash, and that will return information for that process ID. Now I want to go back to another example of showing all processes. And so another way we can do that is with dash E. And we can provide some other fields here that we want to grab. And that way we get a pretty good idea of what's running and some of these other values if we want to run it that way. Again, there's a ton of different specifiers we can provide to the command to return things. We can also provide the sort option, and it can take a field name to sort on. There are also options to specify the type of sort you wish to perform. Check out the man page for more details, but we'll just check it out real quick. We will sort on the command field. So now we have an alphabetical sort there. So as part of our examples, I added priority and nice to the output fields. These are shown as PRI and NI in the output. Before discussing the priority field, I'll run through the NI or nice value first. Nice values impact the priority given to a process on a scale ranging from -20 to +19, with 0 being the default value of a process. The higher the value, the lower the priority. For example, a niceness value of -20 places the highest priority on the process versus 19, which places the lowest priority. To illustrate this, I'm going to use the watch command combined with The ps command, watch will update at specified intervals by rerunning the command. I'll include the -n parameter and pass the value of 1 to update every second, as well as the -d switch so that the changes are highlighted on the terminal. So I'm going to go ahead and just get this running over here. And then on another terminal, I'm going to go ahead and run my command so that we can see it here. So stress creates two processes, the parent control process along with one worker process to create arbitrary load on the CPU. The default nice value of 0 is used when the processes are started. Percent CPU is at 100 for that process, but only a single core is busy. So I'll go ahead and kill that. And then if I rerun my command and I actually specify 2 cores, now we have 2 worker processes stressing the CPU, and each showing 100% because each is being handled by a different core. And so I cancel that and we'll just provide one last example. And I'm going to go ahead and specify 4 so that we get 4 processes here. And so here each process is showing roughly equal CPU time being dedicated. Something to remember here about nice values, regular users can start processes with a lower priority, but cannot launch a process with a priority value less than the default of 0. A regular user can change the niceness of an already running process owned by their account to run with a lower priority, but cannot change it to run with a higher priority. That is, I could start a process with a niceness of 5, renice and change the value to 19, which is the lowest priority, but then I'd receive a permission denied message if I tried to increase the priority by setting the niceness to a lower value. Although I'm not going to demo it directly, I'll show you how the command can be ran on the command line there, and that is nice-n, specify the niceness value that you want to give it, and then the command that you want to run. And so if I wanted to renice a process, I could run sudo renice niceness value, and I could say -10, and then I could run the process ID of the command. So that's what I'll be doing on another terminal, but I want to go ahead and just get our previous watch command up. All right, and now I've got our processes running again. I'm going to go ahead and renice one of our processes here and set it to a value of -10. Go ahead and do that from another terminal. So running the renice command -n -10, and we'll go ahead and reprioritize process ID 1757. Now we can see the results change and more CPU time is being dedicated to the renice process. A case for using nice might be to execute a long-running script on a critical server, running in the lowest priority possible. It is going to run just fine and get all the CPU it needs as long as CPU isn't getting hit hard by other processes. If the application hits a period of heavy use that starts demanding more CPU time, script process can back off and give up CPU time until things slow down. A quick note on the priority field as shown earlier. While niceness is related to priority and changing the nice value of a process does change the priority value, it doesn't completely explain the values that might show up in the priority field. The value here is priority as the kernel sees it. There's a fair bit of explanation required to understand everything going on here, which I think is better suited as a follow-up to build on the basics covered in this video. I'm not sure when I'll get to that video, but if you're interested in learning more, I'll include some links to a couple of articles that provide an overview of the CPU scheduler and how it relates to priority. So I'm going to cover top very briefly here. It provides another way to monitor processes and it automatically updates on its own to provide a real-time report. I'll run it with the -d parameter and pass 1 so it updates every second versus the default 3-second refresh. So that's just top -d1. And top is one of the core tools used for process monitoring. In this video, I'm not going to cover it in depth. There's some summary statistics followed by a list of processes. Most of the fields are the same or similar to the output shown by the ps command. One of the main differences is the CPU field, which displays the percentage of CPU time allocated to the process since the last time top updated, and not the resources allocated over the entire lifetime of the process. It can also be used interactively to manage processes. For example, processes can be terminated or reniced. I'll get more in depth in an upcoming video dedicated to top. Last thing I'm going to cover in this video is killing or terminating processes. Keep in mind that a user has the ability to terminate processes they own, but not those of other users or processes owned by the system. To terminate those processes, you'll need to run commands as root. There are a few commands I'll briefly cover. The first one is the kill command itself. Before we get into demonstrating terminating processes, I'll briefly mention signals and provide a basic explanation, but include a link to more detailed information for those that wish to learn more. The short explanation is that signals are messages that can be sent to processes, and then depending on various factors, the process handles the signal appropriately. We can see all the signals by running the kill command with the $L flag. So, like this. So there are quite a few signals. Not all of them are related to stopping or terminating processes. I'm going to discuss 3 of them in this video since I'm trying to stick to the basics for newer Linux users or those that wish to learn the basics of system administration. First, I'll go over sigterm, which corresponds to signal number 15. It is the default signal sent by the kill command and should be the preferred method because it allows the process to terminate gracefully. Depending on the situation, it may be blocked or ignored by the process, which will prevent the process from being terminated. Let's check out terminating a process normally. To kill the process, I can run kill followed by the ID of the process. As shown in the output, the process reports it was terminated. If I want to specify a signal, I can prefix the signal number with a dash. In this case, I'll send signal 9, which corresponds to sigkill. The simplified explanation is that the signal cannot be blocked or ignored since the kernel destroys the process. The process itself isn't directly sent a signal and does not do any handling. Usually it's a good idea to allow a little bit of time to see if the process will start responding. But if there's no change and then attempts to terminate the misbehaving process by sending sigterm does not end the process, sigkill will likely be successful. Remember, this isn't handled by the process, so it's pretty much blindsiding it. Any operations relating to doing something with data or whatever the process was currently handling will not have a chance to complete properly or abort gracefully. So -9 and the process ID. And this time we get the message killed. And so there's the difference there between attempting to gracefully terminate versus just totally destroying the process. Signal name can also be passed with the S parameter. So I could run it like this. And this time I used sigint, which is the same signal that is sent when pressing Control-C to send an interrupt. Of course, how it is handled by a process will vary when using sigint. I'll leave it to you to learn about the other termination signals and their uses. One last thing to mention about the kill command is that multiple process IDs can be passed to the command to operate against multiple processes. There are a couple of details in the man page that I didn't cover here, so I'll leave it to you to check that out. Another command I'm going to demonstrate is killall. This command provides quite a bit more flexibility as far as options that filter on properties, such as the age of a process, or it could be used to kill all processes for a specific user. It functions like kill in the sense that sigterm is sent by default if a signal is not specified in the command line. I'm going to keep the demo pretty basic here. So I'll start off by launching 3 instances of sleep. I could terminate all processes by specifying the ID of each process with the kill command or use killall, with the name of the process to terminate them all. And there with the -v flag, we get some verbose output, and that way we get a little bit better idea of what's going on. Another example is terminating all processes associated with the user. So we'll log in with another account. Go ahead and run some sleep commands. So here's our processes. And over here, I'm going to run killall-u Bob. So it'll look like this. And so I can see that I ran the killall, but it didn't kill bash. So here's an example of bash ignoring the sig term. And so in this case, bash handled the signal and did not kill it in ending Bob's session. I could have used sig kill, but that's okay. There's just an example of how that might work. And so just one more thing to note about killall is while it can be helpful to get rid of all instances of a process by name, it can also unintentionally kill processes. So you have to pay attention to what's running before executing it. Again, there's a lot more to killall, so check out the man page for more details. And finally, the last command I'm going to cover here is pkill. It shares a man page with pgrep and pid-wait. Though some of the operations listed do not apply to all commands, I'm just going to show a couple basic examples. Run a couple instances of sleep again. And like killall without arguments, it will send sig term to all instances of the name process. And so I mentioned some of the other commands. Another command that can be pretty handy is pgrep. We want to find out the ID of a process. Now we have it right there because we sent it to the background. But if we just knew the name of the process and we wanted to get the ID of it, there we go. And another way that we can get all processes running under a user. There we get all the IDs. And if we want the names as well, we can include -a. And so there we go. There's some basics about working with and managing processes. Some of the topics here have quite a bit of depth and were only briefly covered. I also brushed over some of the tools. I wanted to keep it mostly high level and focus on some of the more basic concepts and management tasks. I plan to follow up with future videos that get into a bit more depth on some of these topics. There are a lot of tools for managing processes and monitoring performance, and I plan on covering some of them in the future too. That's it for this video. Please like and subscribe if you find this content helpful, and let me know what you think in the comments section. Thanks for watching.